Okay, welcome to Mr. Dahlstrom's Pre-AP Physics 2021, the first notes of the year, at least video notes of the year. Hopefully you've been keeping up with the reading in Chapter 6 of the book talking about work and kinetic energy and gravitational potential energy. The one notes we haven't gotten to thus far before we can start talking about conservation of energy is elastic potential energy. So there's kinetic energy, there's potential energy, which is stored energy. We talked about gravitational potential energy being something where by raising some object like the roller coaster game, by putting it higher up on the track, it has more gravitational potential energy. The more energy it has, potential energy it has, the more kinetic energy it will have when it goes down and transfers that energy. Elastic potential energy is usually related to a spring, although it can be anything that can be compressed. Usually anything can be compressed a certain amount. So if I compress this ball, the amount of force, the amount of distance that I compress it is related to how much energy it can store. When I let go of it, it will want to move and transferring it to kinetic energy. So in a spring, we have elastic potential energy, which is in joules, equals 1/2 kx squared. K is the spring constant, which we'll talk about in a second. So it is a constant. Any spring that we have, and I have various different springs here we can look at, depending on basically how stiff the spring is. So this is a very low spring constant because it doesn't take much force to stretch it, compared to this over here, which takes it's not easy to see, considerably more force to stretch it. X here is the displacement, and we talked about this a little bit in class where potential energy here is a scalar which does not have a direction. X, or the displacement, does have a direction, but because it's being multiplied by another variable has a direction, those cancel out and we get what's called a scalar. So that means that there's no direction on that, just same way there's no direction in kinetic energy and there's no direction in gravitational potential energy here. So let's go ahead and talk about what the spring constant means. So lowercase k is the spring constant. Its units are Newton over meter. So you can think about it as that if we're wanting to stretch, let's say a spring 1 meter, the more force that it takes, the more newtons that it takes to stretch it 1 meter, therefore the bigger spring constant. So something like a shock absorber on a car is going to have an enormous amount of force that it takes to move, because if it didn't, your car would bottom out, or you would have it would be very bouncy. Something like a slinky has an extremely low spring constant, to the fact that even when you let go of a spring of the slinky, it just falls. It takes very, very little force to stretch that. So a high value, it takes a lot of force to stretch it. Therefore, the more force it takes to stretch it, work equals force times distance as well, the higher the spring constant, the higher the potential energy. So it's based on how far you stretch it or compress it, and how stiff the spring is. This is all related to what's called Hooke's law, and we didn't talk about this when we got to forces. I wanted to leave it till later. We'll bring it up when we get to oscillations and springs later. But Hooke's law is force is equal to negative kx. We're not going to show the derivation of this right now, but force is in newtons. K is the spring constant. It's the same thing as up here. X is displacement, and K is the spring constant. And the reason we have the negative here is to really, because X over here is a vector, it has a direction, force also is a vector, it has a direction. And so the negative number means the direction of displacement, so we can look down here, is the opposite direction of the force. So if I compress the spring in this way, there's going to be what we call a force, or a restoring force, that's going to try to push it back to where it started. So there's some point of equilibrium. It's a little bit hard to show this here. I'm probably going to include maybe a video link to show this here, but if you imagine that there's a specific place where the block and the spring, we're assuming this is frictionless here, if we compress it here, it's going to want to fly back and forth and will start oscillating. So there's a point of equilibrium. When we push it away from that, there's going to be a force that's trying to restore it back to where it's at. So by pushing it in the negative direction, the restoring force is positive. So a negative x times a negative k will give us a positive force. Vice versa here, if I stretch it, or if I elongate it in the positive direction, the restoring force is going to be back to the left. And this is why we get an oscillation, because every time it goes to the left of the equilibrium, there's a force to the right. When it goes past the equilibrium and it goes to the right, there's a force back, and that's actually what causes an oscillation back and forth or up and down. I think what I wanted to try to show you here, and I'm going to try my best to show it, is that, let me grab some other springs here. They got a spring set. So one of the things that's kind of interesting, I'm going to back away from here and try to refocus this and take this off the side, is I have two different springs here, and if I connect them together, this is getting a little weird. Let's see if I can get that. It's a little wonky, but if let me grab another one here. See how well this works. Yeah, sure. Okay. So if I connect these two springs together, Newton's third law says that whether I'm pulling this one or I'm pulling this one or I'm pulling both of them, the force that this applies on this is equal in magnitude and opposite in direction as this applies on this. So in the Hooke's law equation here, the force on the left is equal and opposite to the direction of the force on the right. What I'm trying to show here is that if we ignore direction here, the bigger the spring constant, and I believe the one on the right is a bigger the spring constant, if the forces are the same, and I can show you this real quick. If the force is, if the force over here is equal to the force over there, then in this case here, a small spring constant will allow a very big change in direction or displacement, and a large spring constant will cause a small displacement. So let's see if that's the case. Where, so this one on the left has a smaller spring constant, so it should stretch more. This one on the right has a bigger spring constant, and so it should stretch less. So when I pull this, let me try to clear here. When I pull this, you can see it doesn't matter if I pull the left one or I pull the right one. We can see that if I pull them here, the one on the left is going to stretch much further than the one on the right. Let me try to make it a little bit more obvious here by using a much stiffer spring than this. Okay, so same thing. If I pull it here, this one on the right, because the spring constant is so much more, is not going to stretch as much as the one over here. So we can see that. So showing that relationship to the spring constant, that the stiffer the spring with a certain force applied, the less distance it's going to have. So we're going to wrap that up as just a tiny little video here about that, and then our next video will be about conservation of energy.